Here we have Bernoulli's equation, which relates the 1/2 rho v squared and the pressure and the rho gh. Now in the previous problems we've seen that rho gh is related to pressure and 1/2 rho v squared is related to pressure. Bernoulli's equation states that 1/2 rho v squared plus rho gh plus pressure is constant in any fluid in any confined fluid when there is no dissipative force at work. This is an ideal case because there are usually dissipative forces, but this is still our first approximation when we analyze fluid problems involving pressure and depth and velocity. Now, it's fairly easy to see that if the pressure is constant and if this whole thing is constant, then these two terms will be constant. That is, 1/2 rho v squared plus rho gh has to be constant. If this is constant and this is constant, then the sum of these two has to be constant. Now that means, of course, if the sum of these two is always the same, then if velocity gets greater, then 1/2 rho v squared will be greater, and to keep the thing constant, rho gh will have to be less, which in general means that h becomes less. Okay, the altitude will decrease. Or if the altitude decreases, that's going to tend to increase the velocity, again, if the pressure is constant. So we see that a greater velocity implies a lesser altitude. A greater altitude implies a lesser velocity. And our paradigm situation for this is simply the tube or container with water in it and water flowing out the bottom. Up here, h is greater and v is less. The fluid up here is not descending very fast. It has essentially zero velocity if we have a large container. Down here we have a significantly greater v, many times, maybe 100 times as great as up here, and h is of course less. So as h decreases, v gets greater. Again, if pressure is constant, and let's note that the pressure up here and the pressure at the exit would presumably be atmospheric pressure. Another situation is where the velocity of the water is constant. This basically usually means that we've got a stationary fluid or fluid flowing through some container at a constant velocity. Okay, we'll think of a stationary fluid right now. Now if that's the case, then P plus rho gh has to be constant because your 1/2 rho v squared is constant if v is constant. And we're assuming that we have constant density here. We're assuming basically liquids. If we get into gases, that's a little more complicated, and that's really beyond the scope of what we're talking about at this point in the course. Okay, so if P plus rho gh is constant, then a greater pressure would be associated with a smaller h, and a lesser pressure with a greater h. Now what does that mean? Well, let's just say we've got a container full of a stationary fluid. Now let's say we've got a tin can in the fluid. Okay, if where h is greater at this point, the pressure is less. Now when h becomes less, the pressure becomes greater and crushes the can. And it's clear, of course, that as h gets less, we go deeper into the fluid, and we know that there's more pressure as we go deeper into the fluid. Another situation where h is constant. If h is constant, then 1/2 rho v squared plus p will be constant because the rho gh term will be constant. And this means that greater v means less p, and lesser v means greater p. Okay, so greater v, less v, greater p. Okay? Typical situation, water flowing in a pipe. Here you have less velocity because the pipe is bigger. The water doesn't have to flow as fast to get through the pipe. Here the pipe is smaller in cross-sectional area, and the fluid has to flow a lot faster. Again, we're assuming a liquid which doesn't compress, so that the amount of liquid passing a point here has to be the same as the amount passing a point here. Since the tube is thinner here, it's got to be moving a lot faster than it does here. Now, if there's less V, that means there's a greater pressure. So you have greater pressure here where the fluid is flowing more slowly, and where the fluid is faster, you have less pressure. Now that's sometimes a little hard for people to understand. It seems like it ought to be the other way. If we have more pressure on the left over here, then there's more force on the left on any element of water that's being forced into this tube. More force on the left than there is on the right, because there's more pressure from the left than there is from the right, which means that the water accelerates to the right. So as the water accelerates, it's because there's more pressure to the left than to the right. And the water certainly has to accelerate to get into this thinner tube. So there has to be less pressure here than here. Otherwise, the water wouldn't be accelerated in this direction.